In calculus, we learned about many different series. We learned about from the simple arithmetic series, geometric series, to the complex and intricate Taylor and Maclaurin series. In this example, we will be learning about a classic representation of the geometric series in real life. Here's our problem. Carter Sanders is a brilliant scientist. He wants to examine bacterial growth in a petri dish filled with water. Each day, the number of bacteria in the petri dish doubles. On the 10th day of Carter's experiment, how many bacteria will be in the petri dish? And we must assume unlimited space and nutrients. We will start with 1 bacteria in the petri dish on day 1. On day 2, the number of bacteria in the petri dish will double. On day 3, again, the number of the bacteria in the petri dish will double. Day 4, again, the bacteria will double. Soon, we begin to see that each day has a common ratio of multiplying the preceding term by 2. So to make this visual, times 2, times 2, times 2. We can begin to write a representation of this geometric series. Let's complete this day-to-day series first. Day 5, it will have 16 bacteria. Day 6, 32 bacteria. Day 7, 64 bacteria. Day 8, 128 bacteria. Day 9, 256 bacteria. And finally on day 10, there will be 512 bacteria in Carter's petri dish. Now again, we are multiplying each of the preceding terms by 2. In the real world, bacteria may also grow like this. For example, in a pond, there will be 1 bacteria. With adequate nutrients and sunlight, or whatever nutrients those bacteria need, it will double. Those 2 bacteria will split into 2 more bacteria, which will double and create 4 bacteria. Now, after a certain number of days or time, those bacteria will each split into 2 and form 8, then 16, then 32, and so on and so forth. Of course, in the real world, there are not unlimited nutrients and space like in our problem, so eventually they will reach a carrying capacity, which means that this geometric series will eventually reach some certain number in which the environment cannot sustain or hold those bacteria. But for our purposes, we are assuming unlimited space and nutrients. So we can form a formula based on this geometric series to estimate the number of bacteria on the nth day. So on the first day, there was 1 bacteria. So 1 is actually 2 to the 0. Now on the second day, there were 2 to the first bacteria. On day 3, again, there were 4 bacteria, which is also 2 squared. Day 4 is 2 cubed bacteria. And again, we begin to see a pattern emerges. On the first day, there were 2 to the 0th bacteria. On the second day, there was 2 to the first bacteria. On the third day, there was 2 to the second bacteria. On the fourth day, there were 2 to the third bacteria. And continuing our sequence, we can see on the 10th day, there were 2 to the 9th bacteria. So our geometric series representation for this population growth would be the bacteria on the nth day is 2 to the n minus 1. Now let's say Carter wanted to extend his experiment to another 3 or 4 days. So we would simply plug the 13th day or the 12th day into our formula. Now let's find the number of bacteria in the petri dish on the 12th day. So day 12 would have 2 to the n, which is our 12 minus 1, or 2 to the 11th bacteria, which is 2048 bacteria. This is a classic representation of a geometric series in the real world.